All right, hey folks. So this week's going to be pretty fun because we get to be critics over other people's work. And what we're going to do is we're going to talk some more about some of the inference, and then talk about how you can actually try to, um, how in practice you deal with trying to actually make causal inference, and then talk about some of the pitfalls that you run into. All right, and then I'll show you some examples uh, of studies that have fallen into the pitfall. I'll even criticize myself a little bit too, even though that's no fun. But then after that, then we're going to go in and do a little bit more work with looking at categorical predictors. And then finally, at the end, we'll talk some about multicollinearity and non-identifiable models, which is kind of an interesting thing. All right, and we get to criticize some people some more, so that'll be fun. All right. So without any further ado, let's just remind ourselves where we were. Where we left off was we had gone through the effort of designing of talking about directed acyclic graphs, and then using those to block paths using multiple regression to actually get at the causal effect that we wanted. Right, and so we said if we wanted to actually do causal analysis, the first step and the first way that we could do it was by doing it statistically with DAGs and things like that, right? So we could handle it statistically. Right? There are statistical methods for dealing with causal inference. And that's purely statistical, right? And so these are things like multiple regression with DAGs, right? So DAG plus multiple regression, which is a fairly crude way of doing it, but it's okay. There are many other ways to help account for this, and this is specifically talking about with you have some data like some observational data. How do you do this? So the first way was DAG, multiple regression. There's also plenty of other ways. We'll talk about some of them near the end of class, near the end of not this class, but of the actual semester, such as regression discontinuity. Continuity. There's things like instrumental variables. There's also other techniques such as propensity score matching. There's all sorts of stuff, right? Propensity matching. I don't know if I'll talk about that one in this class. It's used a lot in a lot of clinical trials and stuff, which is pretty interesting because usually with those, this is particularly useful when you can't get when there's a lot of heterogeneity in the population, where there's lots of differences and things that are really important, lots of different confounds, and at the same time you don't have that large of a sample size. And so what you kind of try to do is you try to find people who say you gave the drug to that you're wanting to see if it's useful. And then you look at some people that you didn't give the drug to, and it wasn't like a random thing where you flip the coin on who got it, but it was just like, okay, the doctor said, this person's doctor said, oh yeah, let's try out this drug for you. And of course, they end up saying that to people who might need it more or might they suspect will benefit from it more. And so the problem is that you end up getting these things where you have a lot of confounds and you're trying to figure out how effective this drug is. And so what you can do is you can try to take somebody who got the drug and try to find someone really similar who happened to not get it, right? So you try to match them up according to how likely, how similar they were and based on how likely they were to get the drug. And so it's like, okay, most people who, had diabetes got the drug, but this one person didn't. So let's match up one of the people who got the drug who had diabetes with the person who didn't get the drug and had diabetes. And then we'll use them and see if one of them fared better than another. So you try to match them up based on how likely they were to have gotten the drug that you're trying to analyze. With these two, I'm not going to describe them too much right now because we're actually going to talk about them in class. But since we're not going to talk about this one in this class, I thought I'd just mention it. If you end up looking at medical research, you'll oftentimes see this used. All right, so anyway, so one, you can handle with statistics. The second way is that you can actually build a theoretical model. And I know I've talked about this I don't think that's how you spell theoretical. theoretical model. And so I believe in the previous week I mentioned that statistical models are oftentimes called reduced form models in econometrics. And then here, theoretical models are oftentimes called structural models in econometrics. And we're going to talk more about this later today. That will be at the very end of class. I'm going to actually go through, we're going to, as a class, do a model and actually estimate it and stuff on the height versus weight data that we've been dealing with. So I actually do a theoretical model on that one. And then I'll also show you one of that UCI put together for COVID projections in Orange County. So I think that'll be pretty useful too. And I'll show you kind of a little bit of how that works and what they end up getting out of it and why theoretical models are typically going to be much better than doing it in any of these other ways. Statistical modeling and theoretical modeling just ends up just outclassing it in general. All right, although sometimes it's really hard to do this, which is why a lot of people fall back to this, because this is sometimes too difficult to realistically do. All right, and then a third way that you can try to get at some causal analysis, and this is one that I use probably most often, given that I work in experimental economics, is experiments. Experiments, or also you could also call them interventions, depending upon how you do it. I missed a few letters there. Interventions. I want to spend a few minutes talking about this. So with an intervention, it's let's go back to our classic example here, which is temperature, and then you have ice cream sales and crime, right? And that was some confound. And one of the things that we argued about was that, well, we knew that if you actually went in and even though you see a correlation between ice cream sales and crime without including if you don't include temperature, if you would actually go in and manually change how much ice cream is being sold, say like closing the ice cream stores, right? Or giving a coupon so that way they would sell more, you wouldn't suddenly see an increase in crime from the coupon or a decrease when you close the store because you're saying that there really isn't actually any causal effect of one on the other. And so that is getting at the idea that if you actually were to intervene or conduct some sort of controlled experiment on where you change the amount of ice cream being sold, you wouldn't be seeing a corresponding change in crime. And so this gives us a hint as to what this stuff is what experiments and interventions actually do, and how if you actually try doing it, it'll help us reveal the causal effect of one another, right? If you can actually do it. Lots of times in a lot of like medical stuff or a lot of other fields, it's unethical to actually manually intervene. If it's something like, okay, we want to know how much your income affects things, right? You can't go there and take a rich person and say, well, we're taking away all your money for this experiment. And so for the next 10 years, go live, in a homeless shelter. You can't do that, right? That would be unethical. And so, or lots of these medical things, we're going to give you this drug even though you don't need it. You know, and so lots of times you can't do it, but luckily in a lot of our stuff we can. And for this ice cream one, you could probably in theory do this, right? I mean, sure, it might lead to some kids crying if you shut down the ice cream stores, but we can live with that. So let's talk a little bit about how you might go about doing this, and I'll talk about how you might conduct one of these interventions, going from kind of the worst way to some of the better ways. So, and I'll explain why they're better versus worse. So, the worst way you could do this is, let's say that you talk to Baskin Robbins or something, or let's go with Cold Stone. You say, hey, Cold Stone, I want to do this experiment, or I want to see if closing down the ice cream stores, leads to less crime. So what I want you to do is just close down half the ice cream stores, and then what we'll do is we'll check out the crime in the area around that half of the stores, and we'll compare it to the other half that stayed open, right? And we'll see if the crime was lower in the ones where they were closed. Now, if you don't say anything and you just say just do it, and you say okay, and then Cold Stone's like, well, okay, we'll pick some to close, and they happen to close all the ones. They go, well, let's close the ones that we think are going to be least busy because we don't want to cost our business too much. So they end up closing all the ones where it's really cold out or it's wintry because nobody's going to buy from them, and they keep the ones open that where it's hot because they expect those to make a lot of money and they don't want to cost them a lot of money. Well, now unfortunately you haven't really done anything because now you look at the ones that were closed down, and of course because it's really cold and wintry there's not much crime, and meanwhile the ones that were opened up that stayed open, there was hot out and there was more crime. So you might compare the two and go, oh yeah, there is more crime when you have ice cream stores open. So you can't do that, right? That should be kind of obvious, right? You can't just, because you're not getting rid of the when you let them choose, you're back to kind of observational data where they happen to choose based off of the temperature, right? The temperature chose which one's closed, right? Or the treatment that you did, right? The intervention, because you left it open. And so now suddenly, you're back in a world where the where you haven't really closed anything, right? You haven't really solved any problems. But let's do something a little bit more reasonable then. Let's suppose that a second way, which would be much smarter, of course, and the standard way would be you say, okay, we're going to look at all the cold stones and we're going to flip a coin. And if it's heads, then it's closing today. And if it's tails, it can stay open today. And we'll look at the crime in the local area. Now, that will actually work. In general, when you do this, so randomization is a really pretty important thing, right? Although it's not the only thing that you can do, right? I'll stress that in a moment, but randomization is pretty useful. Because what will happen here is that if you're just flipping a coin across all the cold stones, there's on average, some of them that you close are going to be where it's cold, and some of them you close it's going to be hot. Now, is there any reason to suspect that it will be that the ones that are hot are closed more often than ones that are cold out? No, right? You would expect that the ones that stay open versus closed, it's random how much of them are hot versus is hot out or cold out. And in general, because you're doing it just by flip of a coin, for it to be, if you say have 1,000 stores, I don't know how many cold stones, like probably not that many, probably more like 100 or 200 or something. I think a lot of them closed. But about 200, right? If you're flipping the coin, the odds that all the hot area ones stay open and all the cold ones is closed is like the equivalent of getting like 100 heads in a row. It's very unlikely, and in general, it's going to even out. And so what this does is that even if there's other things besides temperature that are a confound, suppose that there's some other confound that leads to the two, such as if you were doing this worldwide and this was something like the season or whatever, right? I don't know. I'm making something up here, right? This one isn't too good of an example, but if you're doing this worldwide and the season an equal amount of southern hemisphere, it would even out on average also. Even if you didn't have it in mind, it would even out. Season is actually a little bit of a tricky one because really it's over time, and so you got to be a little bit careful there. Luckily, it's probably the same across all of them at the same time. But anyway, but you can come up with some other confound. We'll just call this U1 or something like that, right? And on average, when you're going to be flipping coins, once again, they should be evened out. The value of the confound should be even across the two treatments, those that stayed open versus those ones that were closed. That's just by chance. So randomization helps by actually controlling, or by evening out any of the confounds. That way, when you compare the two, it's not like somehow they're uneven and you're going to pick up some correlation. All right, so that's nice. But what we did with the randomization here was across stores. There was a different way that we could have done it. We could have said, all right, what we're going to do is for the next week, all cold stones are closed, and then the following week, all of them are open, right? You could do that. And now what you're doing is you're not even doing randomization at this point, although you should still do some randomization, which I'll explain in a moment. But now what you're doing is that you're controlling for everything by having it be the same store that's being closed and open rather than different ones. Now you do have to worry a little bit about, well, what if, it's cold the first week and then hot the second week? This is something that happens like nationwide. Well, then you're going to get some skewed results there. So you want to be a little bit careful about order. So one thing that you could do, though, is you could flip a coin and say, okay, all the ones that I flipped heads for, you close down the first week and are open the second week. All the ones I flipped tails for, you're open the first week and close the second. So you reverse it, right? So half of them are open the first week, and then the other half are open the following week. And so what that does is that helps pretty much control for everything. Because what's really nice about it is that even if there's some rare thing, like what if some what if some of the cold stones out there, like let's say like three of them out there, are actually like the meeting points for the mafia, right? Something ridiculous like that. Well, if you just do a randomization where you say, okay, some of them are open, some of them are closed, if there's only three of them, but they have a huge effect on crime in the area when they're closed versus opened, then what happens is that there's still a chance of only like three or four of some small number that you end up with, all of them being closed or all of them being open when you do it across the nation. And so, because there's only a few of them, it's a rare confound. Well, actually, in that case, it's actually a causal, right? It's a rare bit of causal. But now what happens is that when you do it on the same store, keeping them open versus closed across time, um, you know that you can actually compare it for each individual store and stuff, and you're controlling for all of them because you know that now when you look at okay, which ones are open versus closed, um, since every store is both open and closed at different times, you're not accidentally biasing things by having small random effects be on one side or another. And so when you do it where you have both treatments occur to the same stores or the same subject of that you're trying to study anyway, that is called within treatments, within randomizations, or within treatments, right? And in general, within treatments are a huge win because there's always, there's all these differences between the stores, so you're going to get a lot more noise on the effect on crime when you open versus close them. But with a within treatment, you know very clearly, okay, the crime in the area that I before I closed it, what was it? When I did close it, what was it? And you know that everything is the same. The population's the same. All the same people are around. The temperature's about the same. The climate, all sorts of stuff are controlled for automatically perfectly because you're in the same place when you're running the treatment and you're doing it to the same person. And so another comparison to this is imagine if another example within treatment is something like suppose that you had that you were wanting to test out some new type of treads on shoes. What you could do is you could say, okay, here's some random people. They get tread one. All the other people get tread two. And you're going to get some noise because there's a lot of variance across people. So you have to then take the average effect for one group versus the average effect for the other and try to take the difference. But there's a lot of noise in them, right? And you have to figure it out. An alternative would be you give a person a left shoe with one tread and a right shoe with the other. And then you can compare the treads afterwards, and you can maybe for half of them you switch which one's left and right. But now when you compare them, you've controlled for everything right there, right? That this person is kind of like their own twin, where it's like, okay, they walked the same amount, they had a lot of that, so you're controlling for a lot of the different confounds and variances automatically, and you get a much more precise estimate when you do it within. So I just want to stress this is that in general, when you create an experiment, you should try to design it to be a within experiment, a within treatment experiment. It's not always, oftentimes people don't do that in experimental economics. It's probably, I don't know, one third, two thirds, I would guess, I actually do it within. But if at all you can design it to be a within treatment, you should do it because you're going to get much more reliable estimation of things. All right. And then finally, I'll mention one last bit here, which is sometimes when you have smaller sample sizes, you can also do block design. It's sometimes worthwhile to do block design. Which goes hand in hand with randomization. It's not like an either or. And what block designs do is the first thing you do is you split up, you go, okay, well, I know that I have this big confound of, say, temperature. So what I'm going to do is I'm going to take if I'm going to do it not within here, but between, the alternative to within is between. So in this case, between different stores. And I need to choose half of them to be, closed versus open. What you can do is you can take you can first say, okay, find all the temperature ones and split them so that way they have the two groups have equal temperature, not just through flipping a coin, but actually manually say, okay, half and half. We guarantee that half of them are, that each group, whether or not they get the treatment, on average they have the same temperature, right? You can make sure of it. And that's just by, looking at their temperatures and picking out, okay, here's two with the same temperature. Let's flip a coin. Oh, you go in this group, you go in this group, and you kind of go through the whole setup doing that way. And so that way you can oftentimes block on some of the major confounds and make sure that there's an equal amount in both groups. Like I said, that's usually more important for when it's where you have smaller sample sizes. So if you had, say, only 20 stores that you were looking at, or 10 stores, and you might not want it to be, and you might want to control for a couple of these known confounds where you could actually end up with all three of the mafia run cold stones in one group and not the other. You might want to go, or all four, let's say. You might want to go, okay, well, I know four of you are mafia ones, so let's split 2 and 2. And that lets you control for some of that stuff. Have a little bit more control. But beyond that, once you've said, okay, 2 of you are in this group and 2 of you are in the other, you just to flip a coin to see which ones are in which in general to make sure that you don't, that you still have the benefits of randomization for all the other confounds you haven't thought of. All right. So anyway, so that's some of how you might want to be careful when you're designing the experiments and such. All right. So now let's talk about some of the pitfalls. Right? So you've sat there, you understand this, and you've picked some route that you want to be going as far as trying to estimate some causal effect. So where do things go wrong? Well, there's a lot of different places that things could go wrong. One way is, of course, that you want to interpret things causally, but well, as pitfalls. So these are common pitfalls when you actually look out in the literature. Right? So oftentimes you hear some new scientific study, they're making some causal claim. What are the kind of problems that you can see in them? And so the first one I want to talk about is the one that's actually quite common, which is that they didn't actually do any adjustment, right? They make a causal claim, but only correlation was actually established. Correlation, not causation. All right. And so it can be that they tried to, but say, like they didn't quite draw their DAG, or they just forgot to include something that you look at and say, man, they really forgot this important confound. And so now suddenly they're trying to draw some causal conclusion, and it really isn't. It's just a correlation. And so I want to give a couple examples of this from real life stuff. So first of all, a pretty interesting one. There was actually a paper that came out not long ago. Let me pull this up real fast here. It was published in Nature. Here we go. Pull this up here. And I scrolled down a little bit. And the title of it is our favorite thing: Collider Bias Undermines Our Understanding of COVID-19 Disease Risk and Severity. And so this paper goes through, they talk about what a collider bias is, because a lot of people aren't familiar with it, even though, of course, you guys all are, thanks to last week. And so they're giving some example here of students who are accepted to college right here, and then you try to do a correlation between, or you try to do an estimation to see if people with higher academic abilities are worse in sports. And even if in the general population, it's even, once you say that, well, the only way you get into college is either through like being really, being wanted by a sports team within there because you were really excelled at sports, or because you had good academics. Now suddenly you see a correlation there, even though it's not real. All right. And so they go through and they give some examples. So they try to show some example of where you accidentally see connections, correlations that aren't real. And this is the one I want to focus on right now. You're welcome to read the whole paper. I'll make sure every paper I mention, I'll include a link to it in the description of the video here. But this one's quite interesting because you see this come up quite often. And it's a pretty distinctive problem, which is that what they are saying is, let's suppose in their example, they want to know do healthcare workers get worse COVID diseases, right? When they get COVID, is it worse for them? And the reason why this might be is that the people are talking about the viral load and stuff, where if you're a healthcare worker, you have to be in really close proximity to people who are sick. So you might end up getting more of the virus when you actually catch the disease. And that'll make it so that way the disease is more severe for you than, if you weren't having to work in close proximity to people. And specifically, this was really a concern early on in the pandemic before they had all the PPE gear and all the precautions already set up. And so, what you want to know was a healthcare worker, and you want to know, hey, is this correlated with, or not correlate, but does this cause severity, increased severity in COVID? And what this article is arguing is that it turns out that if you want to try to do this study, you're at least early on in the pandemic, you were in deep trouble. The reason why is because, unbeknownst to you, if you just grab some data off the street of looking at healthcare, like you look at a list of all the different people with COVID and their outcomes, how sick they were, whether or not they died, and then you looked at whether or not they're healthcare workers, and you tried to estimate, okay, we're healthcare workers at getting more severe COVID diseases. You would actually be, unbeknownst to you, conditioning on a collider and getting a faulty correlation. And in this case, it would actually make it look like healthcare workers got it less severe than perhaps your hypothesis, that your hypothesis said that it should be more severe, perhaps. You would actually see that it's less severe. And the reason why is because your data is not of everyone who gets infected, right? And, this is infection severity, right? You didn't look at every single COVID infection and then compare the correlation there, right? Just like how if you sat there and you tried to do sporting ability versus academic ability at a college, you aren't looking at the entire population. You're only looking at those in college. Similarly here, right, and those who made it into college, you have this negative correlation amongst them. So here, you're not looking at every infection. You're looking at those that were detected. You're looking at detected infections, right? Detected infections. Now, clearly, people who have more severe infections are more likely to be detected. That's obvious because when you because if you have to go to the hospital, they're going to test you. And in fact, early on in the pandemic, I remember in New York, they had something like a 50% positivity rate, which is just enormous because at that time they didn't have very many tests. So they almost exclusively tested people who were in the hospital and they needed to know, do they have it or not? Because that's going to determine how we're going to treat them. So, almost everyone they tested ended up having it. The other people that they tested, and they were quite careful about testing, were the doctors and the people who worked in the hospital, right? Because there, even if they were a little bit sick, they didn't want them going around and infecting everybody in the hospital. That would just be a disaster. And so what happened was that healthcare professionals were more likely to actually have their infection detected. And even if it was a mild infection, they would often get tested to ensure that they weren't spreading around the hospital. Or at least that's the story that's presented in the paper. I'd have to check to see if that's actually 100% true, but it's a reasonable story, so we're going to go with it for now. And so what happens, unbeknownst to you, is that you're not checking the entire population. You're only checking this detected infection. And look at that. Once you condition on whether or not they got detected, you're conditioning on a collider. You're in trouble, right? Because now when you look at it, the only people that you're actually measuring who aren't healthcare workers are those who are super sick and in the hospital because they're so sick. And meanwhile, among the healthcare professionals, you're measuring not only the people who are, need to be hospitalized because they're sick, but also people with mild cases that just also happen to get tested because they're more likely to get tested. And so because of that, you look at the two groups and you're going to see that the healthcare workers fare much better, have milder infections than those who didn't. But that was because you actually conditioned on a collider. So it's a really interesting problem. And they go through a ton of examples on how just everywhere you look, where a lot of the stuff that's done is on people who are in the hospital. And so a lot of the studies where they only look at people in the hospital, that's already conditioning on a collider oftentimes. And so you got to be really careful. And I'm going to give a quick little example of this, of something similar where you have a selection bias. And this was a story I heard about. Actually, I was at there was a couple. I was talking to a couple of people a few weeks ago. I think it was like 2 or 3 weeks ago, and someone said, "Oh, I just heard this study that said that people who wear glasses are 2 or 3 times less likely to catch COVID." I don't know if you heard this one, but this has been going around on the news. So let me show you this. You'll find this interesting. So if you just search for, let me do this in incognito window, so that way it doesn't show that I already clicked on the link to it. Let's hear COVID glasses. That's all you have to look up, but you're gonna love this, right? Look at this. Here's all the news stories here. It's called nerd immunity. Oh my goodness. All right, wearing glasses may protect against COVID-19, study says. Nerd immunity. Man, they really like this term nerd immunity. That pun is just too much. Study people, of course, these are all like random websites, right? Like just like local TV affiliates, which shows you that this might not be not that reliable. But there's the Independent, which is also not very reliable. New York Post, not that reliable. So luckily, on the good news, it looks like only the less reliable news sources are reporting this, but they report it nonetheless. A lot of places are reporting it. All right, and so you can easily come across this and think, "Wow, glass wearers 2 to 3 times less likely to get COVID." Wow. And then luckily it links to the actual article. And so let's actually read it and take a look real fast. So luckily I already downloaded it because I've been having some internet issues, so I did it ahead of time. So let me pull that over here. There we go. So let's look at this. So let's just spend a couple minutes looking at it and see if we buy into it. Because I'm going to tell you right now, I don't buy into this. All right. I wanted to say as soon as they said it, as soon as they cited it, I was like, that sounds like way too big of a thing for wearing glasses. Wearing glasses cut your odds down by 2 to 3 times. That's hard to believe, right? So okay, amongst spectacle wearing population in northern India. All right, so this is a study in India. I mean, sure they have different demographics than us, but I don't see necessarily why I would assume that would be a big difference. Why it wouldn't be hold true at least somewhat in the U.S. All right. They go through long-term use of spectacles may prevent repeated touching and rubbing of the eyes. That's the thinking. So already you go, okay, so that's how it's protecting us from preventing you from rubbing your eyes. First of all, anyone who wears glasses will know that they rub their eyes all the time. I don't know. What we'll see is that they never do any analysis showing that people actually rub their eyes less when they wear glasses. Um, so I don't know about that one. But also that would also mean that at least half to 2/3 of all transmissions are going through rubbing your eyes. If that's the way that glasses stop you from getting it, assume that you never touch your eyes ever if you wear glasses. Then that means that for it to be actually reduced it in half to 2/3 would require that half to 2/3 are all from rubbing your eyes, which I have not heard established at all. I thought it was mostly through breathing, inhaling, or with the droplets in the mouth or whatever, breathing it in. So that would be news to me. But anyway, so I don't know how much I buy into this already, but we'll take it. This is why my prior says I doubt this. And so let's go through and take a look though. So they have 304 patients who had coronavirus. They assessed whether or not they wore glasses. They compared it to the general population use of glasses. All right, and then they tried to see whether or not it seemed like people who were coming in with COVID were less likely, and they came up with, yeah, it was 2/3, 2 to 3 times less. All right. Yeah, calculated risk ratio, which is they found 0.48 was the risk of catching COVID for those with glasses versus 1.35. You divide the two and you get 0.36. So that means like 2/3 less likely. And a strong p-value too. Hey, hey. So let's go down here. Let's actually get to the meat of it. We don't need to read a lot of this stuff. Oh, now this is something that's useful here. They say the prevalence of refractive errors in India, this is of eye problems here, is 53.1% in adults, and 10% of adults have uncorrected. So that means they're not using glasses. From the data described, we can estimate that about 40% of Indian persons use spectacles. So right here, they've estimated that 40% of people wear glasses. And we'll see that you got to keep this in mind on how they estimate this. They took some previous survey, which said 53% of adults need glasses, which sounds high, but it turns out that that is probably right. It's actually a little bit low compared to a lot of Western countries. But 40% of people end up wearing glasses. 10% aren't actually using it, even though they need it, apparently. So okay, let's keep going. So they talk about some stuff here. There were a total of 313 patients, 17 patients. 304 of them had gotten informed consent. Okay. Inclusion criteria. All the admitted patients of mild COVID-19 whose age ranged more than 10 years were included in the study. People who were excluded were those who were under the age of 10, and also patients having moderate and severe disease were also excluded. That's an interesting thing. They don't specify why they excluded people with severe diseases, moderate or severe. But we'll come back to that because that's an important point on why I think this is actually kind of a weak study. And then they go through a little bit, and they start trying to ask them about whether or not they wore glasses. You can see here's the questionnaire. And what they did from it was they asked, okay, do you need glasses? Do you wear glasses? How often do you wear glasses? Occasionally, only while reading, all the time. Do you wear sunglasses? And do you always do it whenever you go out? And what's interesting is that in the group that they ended up keeping as saying that they wear glasses are those who said that they wear it all the time or who wear sunglasses whenever they go out. Now, it's already kind of weird because you don't typically transmit COVID nearly as much outside, or at least the risk is much lower. So including the sunglasses people in the group actually is hurting the strength of, is actually making it seem like more glasses wearers get it than probably are entirely realistic. Because, well, it brings up a question here, which is that I think in the original way that they measured the prevalence, this is only with people with refractive errors. So there's actually people who need glasses. But in the group of people who wear glasses where they're measuring if they had COVID, they're including sunglasses wearers, which do not need it. So it's actually kind of a little bit of a weird thing already because they're including extra people who, as having gotten glasses wearers who have COVID, but then when they're comparing against, the total population of glasses wearers, they aren't including those people. So it's kind of weird. But anyway, we keep going here, and they end up getting the number of people who wear glasses all the time or wear sunglasses all the time for outdoor activity. Right there, continue behavior of using glasses throughout the day or always for outdoor activity for sunglasses. And then they figure out, okay, now they sit there and they do a little bit of math here and they say, okay, well, all we're going to take is the percentage of people in our sample of people who had COVID who wear spectacles all the time, divide that by the percentage of people in the general population. That's 19 over 40. That means 48%, less likely than you would have expected because 40% of the population wear glasses. Only 19% of our sample actually had glasses, 48% there. Meanwhile, for those, for the other group, it's 1.35, and that gives us a 0.36. Now, where's all the problem with this? Well, the first problem goes back to the problem of doing a selection bias. So they only are looking at people who had mild cases in the hospital, right? Well, that's the first issue. The second issue is they measured these people. The way that they got their data here was by taking each one of the people and asking, do you wear glasses all the time, not just occasionally? And those are the people they include as having gotten COVID here, right? But meanwhile, for this group down here, this denominator where they say 40% of Indians wear glasses, that wasn't glasses continuously. That was just people who wear glasses at any time, including the occasional wearers. Right? If you restricted this to only the people who wear glasses all the time, you would see this number go down significantly. So that alone already probably accounts for a lot of it. Now, how much? I had to look that up. So I pulled up some data here from, this is apparently from the Netherlands, where they actually had some data. This is from, I guess, their statistical group there. I think this is actually a governmental organization. I'm not quite positive on this. And scroll down a little bit and they say among people wearing glasses, 54% of them wear them on a more or less full-time basis. So only about half of people who you say actually wear glasses, where by the way, it's about in Netherlands it's around 61%. But only around half of them wear them all more or less on a full-time basis. So what sucks here is that immediately, if you say, okay, among that 40%, probably only around half of them are actually wearing glasses continuously. Now suddenly it's you expect around 20% of them, and you get around 19% if you do that reduction. Now, of course, there's still that they inflated this number a bit with their sunglasses inclusion. So it's hard to exactly say. It's also hard to say what percentage of people actually wear them all the time in India, because it's different cultures, so it could be a little bit different there. So it's hard to say exactly what the denominator should be, but 40% is almost certainly an overestimation, significantly so. But to make matters worse, is you look at it and you see, okay, they've selected down to only those with mild cases of COVID, and not the moderate or severe. Well, the problem is that is a collider bias right there, because you're selecting a certain group of people. And so you have to ask yourself, well, what kind of people are you excluding when you say only mild rather than moderate and severe? Well, the people who most likely have moderate and severe COVID are older people, right? I mean, that's the number one correlation there is the older you are, the more likely you are to have severe COVID. And so you look at it though, and who's most likely to wear glasses? Old people, right? Where the older you get, the more you need glasses. According to Netherlands here, almost 100% of people by the time they're like over 50 need glasses for at least reading. Oh boy, yikes, right? So you guys get to eventually enjoy what I've enjoyed my whole life. It's really not bad. But anyway, so what's happening here though is that when you think about it, when they're excluding when they're excluding all the moderate and severe cases, they're excluding a lot of the population. They're excluding all these old people, and all of them wear glasses. So that on top of that, if you included the moderate and severe, this number relative to the non-glasses would likely go up because you're including a lot of older people, and older people almost exclusively wear glasses. So now maybe they're more likely to only wear them some of the time, because I believe younger people tend to be ones who really need them and wear them all the time. And so it's hard to say exactly how it all works out. It's really, you actually have to sit there and collect data and check it. But what I can tell you is that this data as it is, just is not enough, right? I mean, it's not convincing me in the slightest, all right? Because it's clearly misestimated both of these numbers significantly by collider bias, and also just by not using the same method for estimating it. One where they use a survey, and the other one they just use some old data that they found around that was measuring something completely different, which wasn't all the time glass wearers, but just anyone who needs glasses. So it's quite or wears glasses at all. So both of these numbers have massive levels of uncertainty and bias in them. So I wouldn't, you know, you could, I had a little pin that said I'm nerd immune, and then I had to throw that out because no nerd immunity. It's not a thing. It's made up pretty much. It's a bad study, right? It's sad, but it's true. At least it's just not a very strong analysis, and that's the way it is. Now, I will say that when looking for this, I found that there was another study done in China, and literally they did the exact same thing. I was amazed. I mean, they did the same thing where they questioned them and said only those who wore them all the time, and to estimate the population that had wore glasses, they just used some old study that didn't condition on only on people who wore them all the time. They did literally the exact same thing as this one did, and I was kind of surprised to see that it was an identical problem. But it is what it is. So that's the first one, which I kind of want to talk about, which is these collider biases and such. So the next one that I want to talk about is so we talked about correlation, and if you aren't careful, you can accidentally get these correlations in there, not the actual causation. A second thing you got to worry about, and I'll show you a couple papers that have had that share some of this and some of both of these problems here is also data proxies. And so data proxies are the case that lots of times you want to measure something, um, like for example, let's say obesity, right? You want to know if obesity has some effect, right? But you have a hard time actually measuring it, because maybe you can't go around and actually measure the people's dimensions and blah, blah, blah. So you use some proxy that's supposed to kind of be close to it. And so use, for example, BMI. And anyone can tell you, anyone who's really looked into it, that BMI is a terrible measure for deciding whether or not someone's obese. Because, for example, a lot of athletes um, have a lot of muscle, and muscle weighs is denser than even fat. And so a lot of the really good athletes that you look at are actually in very good shape, have a lot of muscle tone and stuff, and they're labeled as obese by BMI. And so you're trying to do stuff like, okay, does being obese lead to certain issues like diabetes? And you do it, and you're getting a lot of healthy people who are probably less likely to get it than somebody who's just normal weight, but doesn't have any muscle tone or whatnot. And so they aren't working out, they're sedentary life. This is more describing me. All of a sudden, I'm not liking it. Um, but um, so you do that, and while somebody like me maybe is at even higher risk of diabetes than someone who is labeled as obese by BMI. And so, you use some proxy and it doesn't actually really get at what you're wanting to get at. And so I want to give a couple examples of that. The first one is this kind of interesting one, which was recently actually retracted. It was published in, I think, Nature, and then they pulled it out. They said, "Oh, no, 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 we can't have this." So, and that's because it had some issues. All right, now I'm not going to get into all of them just because I don't have time to do it all. But let me show you this one. So this one was, like I said, you'll see if you try to download the article, like on every single page, it has this big watermark saying retracted on it. And here is retracted article. The association between early career informal mentorship and academic collaborations and junior author performance. So what they wanted to do was they wanted to look at, um, they were looking in scientific, in academia, whether or not, like, how your mentor affected you, right? So for example, for me, I have my thesis advisor, my dissertation advisors, and I worked with them and I published some papers or whatnot, or I'm in the process of publishing papers. And the question is, based on their mentorship, how does that affect me in the future? Right? That's kind of the idea. And they go through stuff, and one of the big effects that they mentioned, that they found in this, is that um, it's something that was quite controversial, which was, we also find that increasing the proportion of female mentors is associated not only with a reduction in post-mentorship impact of female proteges, but also a reduction in the gain of female mentors. And so if you end up scrolling down, you have to go through a lot. There's a lot of various stuff. Once you get down to the discussion section, this is where you start getting some interesting things here, where they start saying that their study fills this gap and suggests that female proteges who remain in academia reap more benefits when mentored by males rather than equally impactful female mentors. The specific drivers underlying this empirical fact could be multifold, such as female mentors serving on more committees, thereby reducing the time they are able to invest in their proteges, or women taking on less recognized topics than that their proteges emulate. But these potential drivers are outside the scope of this study. And they also at some point talk about, I missed it here, but they talk about how essentially they say that those who mentor under women have lower quality output in the long run. I believe they actually use quality several times here. So the first thing is, I'm just going to say right up front, is that when you look at their actual causal inference to actually make these type of statements, such as how this might be caused, such as committees and stuff, there are actually lots of confounds. All right, and they really should not be saying this. This is a pretty strong trying to do these causal inference here when they really didn't do what was necessary to really do that efficiently or effectively. So just to show you, though, that the data, to focus on just one part of this paper, which is the data proxies here. What does it mean to talk about how successful someone is in academia, right? Because that's one of the questions here, which is, okay, what do you mean by reap more benefits? What benefits are you talking about? And what do you mean by mentored anyway? Are you talking about people who are like dissertation advisors? Or are you talking about, because also like postdocs, lots of times you work with some of the faculty closely there too after you've gotten your PhD. Are you talking about how are you measuring this, right? There's a lot of questions here as far as how do you actually get this? Did they send out a survey perhaps and ask people like, hey, how do you feel your uh your career has been in academia? Who was your advisor? Were they male or female? Who would you consider your mentors, or blah blah blah? You can ask that sort of question, and that maybe that's how they did it. Let's actually look at their data and see. So I'm just going to show you, this guy went through and actually pulled up their data, or at least a chunk of their data, the first like 10,000 data points, and tried to do some basic just summary statistics looking at what it talks about. And there's some really interesting things in it. So one thing is, let's see if I can pull it up here quickly. Let's see, I scrolled away from it, unfortunately. Here is Protege's first publication year. So this is the mentee, what year they first published. And then versus on the y-axis, how many mentors they had. And you'll see that a lot of them had like over 50 mentors, right? I mean, there's a lot over 25 even. I mean, you wouldn't think, you would think that most people had maybe like 4 or 5 mentors, but here among males or females, a lot of them just have a massive number of mentors. So what's going on there? What on earth are they even measuring here to get this many mentors? And what it says here is, in the supplement, they say that whenever a junior scientist publishes a paper with a senior scientist, we consider the former to be a protege and the latter to be a mentor, as long as they are authored at least one paper with 20 or fewer co-authors and share the same discipline and U.S. affiliation. So what that says is that they aren't actually measuring mentor-mentee relationships. What they're doing is saying, what they're really measuring is co-authorship on a paper, as long as you're at the same university or a research lab or whatnot, on a joint paper with 20 or fewer co-authors. So if somebody published something where there's 20 people all at this one group at CERN, they're all your mentors now, even if you barely met some of them, right? So suddenly we go, oh, wait a second here. As soon as we find and replace every statement with mentor with co-author on at least one paper while at the same institution, suddenly you are going, well, okay, maybe this isn't quite saying the same thing that we thought, because this isn't exactly, when I think of mentor, this is not what I think of. And they're measuring things that are quite different. Something else that's interesting, as you see, that they also have some data quality issues that they have to fix, where, for example, there was right here, this is the age of the mentor. And you'll see that a lot of times the mentor is like over 200 years old. So they clearly just need to clean up their data some, because somehow they're matching people up with the wrong people, which is a little bit problematic. But on top of that, how are they measuring quality, right? How are they measuring how well you're doing, like post mentorship? And the answer is that they measure it by, I don't know if I can find it here, but I'll just tell you, they measure it by number of citations in papers that you publish. So what they've actually done is they haven't asked anyone anything. They went to all the repositories for published papers, and they matched up mentorships based on these publications. For, okay, here's a new person who just published for the first time, and here's who they published with, so those are their mentors. And then after a set number of years, like 5 years or 10 years, they then looked at all the stuff that the mentee had then published since then, and said, how many citations do they get? Now, anyone who's in academia knows that citation is not always synonymous with how good of research you're doing, right? And so you suddenly have to ask yourself, like, okay, now what we're really measuring is not talking about whether or not your mentor led you to have higher, achievement or quality of research and science stuff in the future. It's more about, did co-authoring with this person lead to more or fewer citations in the future? And then there's a lot of noise in it from some iffy probably web scraping and stuff, or not cleaning your data quite as much as you should have. And now suddenly it turns out that your correlations and possible confounds starts just multiplying, because in fact previous studies have already shown that women get fewer citations than men, right? And it's not necessarily due to some causal effect of women producing less quality research or some stuff like that, but there could be various confounds. There could be various things that are unrelated to quality of the work is leading to differentials in citation counts. And so as soon as you say our mentee with mentor, as soon as you say co-author with a woman, for example, you might in the future co-author with women more often. That might be an indication that you prefer co-authoring with them at times. And then, of course, in the future, that means you're going to get fewer citations. And it had nothing to do with the quality of the mentorship or anything, even if there was one, right? And so it's kind of galling in a sense to sit there and hear them, to have them sit there and go, well, maybe this is because female mentors are having to serve on work committees, so they have less time to dedicate to their proteges, or things like that, which is kind of like, that's really jumping several leaps there without the justification that you really need to be making to be able to do that reliably. And so you're welcome to read this paper. Like I said, it should be underneath. I'll link to everything here. But it's kind of an interesting problem. All right. And it's not an easy one. I want to say that, although it's easy to criticize this stuff, like, how would you actually measure this? Like, try to think of it on your own and get a reliable measure on this stuff. And it's not an easy task. And in fact, the data that they got is probably pretty good. It could use some cleaning, but it's actually a pretty good data set, and kind of interesting to get the citation count and things like that. That's pretty useful stuff that you can do a lot of other analysis on. And so, it's not like this work that they did was worthless or anything like that. All right. Another one that I want to show, and one that just came up recently, and Michael, if you're watching, you'll appreciate this one, because apparently this was a talk that was given over at here at Chapman last year. I didn't go to it, but it's an interesting one where a couple of years ago, it feels like a lifetime ago, Starbucks had called the cops on a couple of African Americans who wanted to use the bathroom or something and hadn't purchased something. I don't remember the entire story, and I'm not going to try to cite it. But they called the cops on them, and then it became a very large media story and such. And then Starbucks announced that, okay, from now on, anyone can use their bathrooms. They're now public. All right, they're public. They're called public goods, where anyone can use them. All right. And so what these people did was they tried to analyze how that affected the sales for Starbucks. And specifically, when you start reading it, they go, okay, in response to some protests, they changed their policy to allow anybody to sit in their stores and use the bathroom without making a purchase. And they're upfront about how they measured this, because they want to know how many people actually go to the stores. And so they actually used cell phone data, location data, which is not, it's not like you don't know for sure. You're basing it based off of some cell phone, which is not necessarily 100% reliable. We estimate that the policy led to a 7.3% decline in store attendance at Starbucks locations relative to other nearby coffee shops and restaurants. This decline cannot be calculated from Starbucks' public disclosures, which lack a comparison group. Because the worry is that, just based on the economy, maybe all places are going up or down, and so you need a comparison. Now, what's interesting is that they haven't yet. This is all fine. You might quibble with the proxy, but they actually go in their paper and justify the proxy to show that it's actually that the cell phone location data is actually a good measure. At least they try to. I haven't read it closely enough to say whether or not I completely buy into it. But so we'll take it on faith here, and that's okay. But all they're saying is that, but now they are doing a causal inference here, where they're saying that the policy led to a decline. That means that they got to make sure that they've closed all the other possible confounds that involved when the policy came into effect and the total attendance at Starbucks. And so let's see how they come up with this causal inference here. So they say the decline in visits is around 84% larger for stores located near homeless shelters. This policy also affected the intensive margin of demand. You can keep blah, blah, blah for a little bit here. And they say these results show that the difficulties of companies attempting to provide public goods as potential customers are crowded out by non-paying members of the public. So what they're ultimately saying with the homeless shelter idea is that once they've changed this policy where people can stay without and use the bathroom without making a purchase, that a lot more, presumably more homeless people have started to show up. And this is driving away business. Where before the homeless people weren't being able to go in because they needed to purchase something. And so now potential customers are no longer being crowded out by non-paying members of the public, by the homeless, is what they're saying here. And the way that they measured this is by looking at how close the stores were to homeless shelters and showing that when they were closer to homeless shelters, they had a bigger decline in attendance or people, in store attendance. So let's dig down here. When I heard this, I'll be honest, I was slightly skeptical. Now I should also be honest here. I have not read the entire paper. But I have read certain parts of their results and things like that, and really checked out their analysis. So I could say some stuff, and they were careful at several times to not make overly strong causal inferences or statements about causation. But there are some issues. And so the first one, let's just scroll down all the way to the data and just skip down to the data and take a look at it, because you'll immediately see some stuff that's a little bit iffy here. Which is, whoa, maybe I should just scroll faster here. Here we go. So first of all, this is when they were looking at comparing Starbucks reported same-store sales growth versus growth in number of cell phone visitors. Now, they don't expect these to match up perfectly because sales can also be through people spending more when they do attend. And so they don't expect them to match up perfectly. And they talk about it in the paper, and they say, well, they match up fairly in line. But of course, you expect some difference where if Starbucks is selling them at higher price or things like that, you'll see higher sales growth than you do actually attendance. But this is the interesting one. This one, to be honest, right when I saw this, I suddenly had strong skepticism about all the results. So what they've done is this is the last 2 years. Of course, everything probably changed after COVID, but they're still blissfully unaware of that. And they bin this into 4 groups. Bin 1, 2, 3, 4, which is blue is 1, 2, 3, and 4, which is how close they are to a homeless shelter. All right. And what they're seeing here is that when you're far away from a homeless shelter, you'll see that this red line is when they implemented the policy. When they changed their policy, you don't really see too much of a difference. This spike is probably due to this is right around Christmas. So my bet is that this is like a Christmas holiday bump, right? But you don't see too much difference before and after, right? In the medium group, you see a little bit of a decline after if you just compare this number after to before. And then for this one, you likewise see, a little bit, you see quite a bit of decline when you're really close. So this is where a lot of their data is driving from. But of course, you immediately see a problem here. Before the policy came into effect, they were already much lower. Things were much lower than they were in the past year. So why on earth did the decline happen? And you can also see a bit of this decline happening over here too, in comparison. Why did the decline happen before they implemented the policy? Were these people like clairvoyant or something and like saw that the policy was coming down the pike and so they stopped going? It's a fair question and it's not obvious, right? It suddenly makes me very skeptical because you compare that to where it was before they implemented the policy and you don't see that much of a difference there. In fact, for the lowest bin here, closest, you see like 0 difference from the closest time before they implemented it to afterwards. It stays pretty steady. And same thing for most of these. In fact, it goes up a little bit in some of them. So I'm already quite skeptical of the results just based on the timing of things, right? But let's try to figure out So if that's the case, though, why did it go down? That's actually a fair question. Why do you see it going down in the closest ones more so than the ones further away? Well, there is one possible explanation. And now I'm not going to say that this is the explanation or anything like that, but it's one that the authors actually considered. And I think that they make it that it's actually a fair case, which is that they're using distance from homeless shelters, right? Distance to homeless shelter. And they're using that as a proxy. They actually say in the paper that, well, look, we don't know where all the homeless people are, right? By definition, it's kind of hard to track them down because they don't have homes. And so what we're using is this distance to homeless shelters, right? And presumably that's going to result that ones that are closer to homeless shelters have more homeless people, right? And that is going to affect the final sales, the change in sales or popularity for Starbucks, right? So we'll do change in yeah, popularity, right? Because they're specifically talking about not sales, but actually attendance. People going there by the cell phone data. And so, before the policy versus after, those that are close to the homeless are going to have a bigger drop off in attendance, right? But here's an alternative thing that it could be, which is that where are all the homeless shelters? A fair question, right? Where, if you, I would say two things. First of all, since their measurements here, I believe that the four groups are something like 0 to 2 kilometers, 2 to 5 kilometers, 5 to 10, and 10 to 20 kilometers away from a homeless shelter, or those four groups. And so, where would you be closest to a homeless shelter? Well, obviously, right next to a homeless shelter. But I mean, in general, are there certain areas where you might find yourself closer to a homeless shelter than others? Well, it could be poorer neighborhoods because, in general, a lot of the richer neighborhoods try to push them out of the say like you aren't allowed to build them here. They don't want homeless people around. That's Irvine for you. And then, but secondly, probably the denser populated areas, right? The more urbanization there is, the higher the density of population, there's just so many people there that you need more. You need more Starbucks. You need more homeless shelters, right? And in a certain area, there's going to be more of everything. And so because of that, you're going to find that the stores are more likely to be close to a homeless shelter. So one of the concerns that they had in the paper was that the density, population density in the area, affected your distance to homeless shelters. One of their concerns were, well, what if what's happening here isn't so much that it's the homeless people driving away people, but rather what's going on is that maybe just in really dense, in like the very dense parts of cities, very urban centers, for some reason, one reason or another, uh, Starbucks is losing popularity. So, for example, around here at Chapman, in the circle, right around this time, like a couple years ago, there were we've always had two Starbucks that are literally across the street from each other. It's amazing. But we had several new coffee places open recently. There's like Phil's Coffee. There's Koala, was it Aussie Bean? I think it is. That one's closed now already, thanks to COVID. But there's another one like 1886 or something. There's been like several ones opening up recently over the last several years. And so it could just be that there's a rise in boutique coffee shops. And those tend to be at the most like kind of more affluent or just more urban centers, maybe not affluent, but the urban areas. And so it could just be that Starbucks is losing out to them, right? And then in the more rural areas, they're not. I mean, those more specialty shops haven't opened up there. And so you could have that sort of issue here. And if that's the case, now suddenly the density is causing the difference. And now if you try to just try to do a correlation between distance from homeless shelter and change in your popularity, you have that direct causation path, but you also get this fork that's confounding things. So you need to make sure you include it. So let's take a look at their regressions and see how it turns out. All right. So they do some. Now the good news is they actually considered all this and they ran some of their regressions on this. And what you'll see is here is, let's see here. This one's just doing it with some of the stuff. Let's go down to table 3 here. So here what they're doing is they're looking at Starbucks post the change, and then they compare, and they looked how much does it change with distance. And so it's a little bit hard to read all this stuff because it's all normalized, and I wish they kind of converted a lot of this stuff back into uh, easy to read. And they might have done it in some parts of the paper, and they did in some parts of the paper. But I wish, in general, it was easier to understand exactly what all it's saying. But in general, what it's saying is that Starbucks, after they implemented this policy, had a decrease. If you compare all the periods afterwards compared to before, they had a decrease in the amount of popularity, right? But then the further away you are, their popularity goes up. The further away from a homeless shelter. All right, and that one's positive. Now, already I'm a little bit concerned here. I'll have to read a little bit more on this, but you can see that for other restaurants, so this includes restaurants and other coffee shops, the closer they are, the further away that the worse they do from a homeless shelter. So if you're trying to interpret this proxy of distance from homeless shelter as being the amount of homeless, and that's causing these effects, it would be awfully strange that the closer that restaurants and and other coffee shops are to homeless shelters, they do better and better business. That would be kind of an odd thing to think about, right? Oh, the closer they are to homeless people, the better they do. Now, it could be, I'll have to read a little bit carefully, because I would expect that, you could say, well, Starbucks is losing business to these guys, right? Because of their homeless policy. And so you would expect it to go up in those areas where Starbucks is losing out. But so I'll have to read it some to see how they normalize everything. But my hunch would be that the effect of some people not going to Starbucks, a 7% decline going to other places, they're spread out across all the other restaurants and coffee shops. So you won't see all of them go up by a whole bunch, and which this seems to indicate. So I'm a little bit skeptical of it. But okay. But then they do a little bit extra analysis where thankfully they try to include visitor density and store density in their uh, models. And we see that, yeah, sure enough, density is a pretty significant thing, right? Not entirely, but pretty significant. And more than that, if you look up here, compare the results beforehand, where you have to interpret all this stuff with all the stars and everything, rather than just some nice, well, they don't give confidence intervals, sadly. But they give you the p-values here, and so you can kind of backwards induce estimate. These are the t-statistics, so you can kind of backwards estimate if you really want to. There's a lot of variance in here, right? But what you'll see is that once they go from 2 stars, which says it's pretty strong effect, I'm guessing. I have to look at it. Once they include the visitor density, a lot of stuff ends up going away to some degree. And specifically right here, you'll see that a lot of the effects get weakened by quite a bit. And, it's kind of the nature of the beast, which says that at least partially this stuff is being confounded. And so between this, with the extra confounding effects, the 1 star means as a weaker, they say it's still an effect, but it's significantly weakened. And so they're saying, so they say they're robust, but it's like, you're definitely picking up some correlation at the very least. And then on top of that, you have this problem of the foresight here, where they've lost a lot of their business before they even implemented their policy. And I'm starting to have some doubts on it. And so my point on this is that, this is a pretty small thing here, right? I mean, this is a small effect. It's just like 1/4 worth of difference here. But, anything wrong with it or anything suspicious makes the reader suddenly not really necessarily believe all the causal impact that they're talking about. And you got to get everything right. It's really hard to convince someone of a causal effect, right? It's very easy to have little bits of holes in it. And so one thing that I should say is that with this one, I'm not going to put this in the, I don't believe it at all. It's kind of more in the middle, where I'm not quite sure yet what to believe entirely. And I'd like to see some more analysis before I really have a strong belief one way or the other. So, so one of the things that you have to do as you're reading papers is you have to be a judge on how severe are the problems that you find, because every model has problems. Every analysis is going to have little things like quirks and things like that. You got to decide, is this a fatal flaw or not? And it's not always easy to make that decision. I've seen some people write up some paper talking about some of the Pfizer results for their vaccine, coming up with little tiny essentially nitpicks and saying, oh, well, now the whole thing's questionable. I don't believe any of it. And it's like, man, this thing wasn't like borderline whether or not, it was a positive or negative effect. I mean, the vaccine was like, a million standard deviations over. It wasn't quite that high, but a lot of standard deviations over, and this was a huge effect. And so even with little nits, it's not going to suddenly ruin the results, I don't think. But anyway, that's another example of something where, like, this was more of a middle ground. They did actually, if you read the paper, they did a lot of really good work and a lot of careful analysis. But even still, it's just tough to really show this stuff. All right. And then, so one thing I will say though is that you're always kind of tempted. And so now I'll pick on myself real fast. You're always kind of tempted. Let me just get this started back up again. You're tempted to always kind of believe these surprising results. And, it turns out, that's what gets shared by a lot of people. You see something surprising, you share it with people. It's like, wow, I didn't believe this. I couldn't believe that glasses reduced your chances of COVID so much. So then that's how this stuff spreads around and gets into all the news. But I had this happen to me where I fell for it and I kind of spread something that was probably misinformation at the end of the day. It was. Uh, and so I felt really bad and I had to go sheepishly apologize, say, oh no, once I found out. Because what happened was that I had seen some link and it was a reasonable source that had talked about how on an aircraft carrier they had gotten, there's a COVID outbreak on an aircraft carrier. And they had actually, so that way it was actually a good case study because they was able to, actually measure when people got it and all their symptoms and stuff like that. And it had shown their symptoms by frequency when they first started. Now, of course, it's a biased sample because young people. But I was like, hey, you know what? They're probably around my age. So, if I'm curious about what symptoms I can expect to see, I can use this, and so can my friends. And so I looked at it, and it was a very surprising result. It showed that fever was only like, at initial onset of the disease, it was only like 20, 30% of people had fevers. It was incredibly low compared to like headaches or loss of smell, which was more like 70%. I couldn't believe it. I was like, sure, like, whoa, look at this. They have us take us their temperature every day, and it's not even that common. And then, like a week or two later, I was trying to look this stuff up again, and every source I could find was saying fever 80% of the time. And then, so one of the things that's interesting is that now, in my defense, it turns out that there are a lot of variants. And so this is at the CDC's government website, where they list frequency um, of these different symptoms. And you'll see that, based on the study, they get very different results. So like fever, somewhere between 44 and 91% of the people show it, right? Depending upon which study you look at. Some of them say only 44%. I think one of them was in Europe. There's this European study that seemed to be kind of an outlier. Where, yeah, you can see a larger cohort study in Europe found only 45% of cases had a fever, versus in China where some were 80%. And the US CDC pegs at like 80, 90%. Cough, another one range. But then some of the really interesting ones are things like loss of appetite or loss of smell. And you get down to like headache. Depending on where you look, some say it's 6% of people, some other places say 70% of people have headaches. It's just incredibly huge amount of variance here. But in general, I happen to just look at one that was probably skewed. And for the record, I can't even find it again. So it might not even been legit for all I know. And I was spreading because, like, oh, look, this surprising result of fever being like 20%. It was even lower than this, than the low end of any reputable study. And so I'm like, well, you know, oh, now I gotta go back to all my friends and apologize. So it's very easy, and they always say that surprising results end up getting sent around the news a lot more, and people end up sharing them a lot more. So be careful if you hear something surprising. You might want to dig into it a little bit more, or find some other source for you, and make sure it really is true. Because a lot of this stuff, or dig into the data, open up the paper and take a look. Usually you can find them. All right, so that's just a little bit of a word of warning for you guys. So now I want to do one other extra bias here, or place. Ooh, I erased it all. So a third thing is very often, and this is a part of the thing with actually that previous study I was showing you, is that lots of times you end up with very large uncertainty intervals. Um, and so, or confidence intervals, or credible intervals, or whatever you want to call it. There's a lot of uncertainty in your estimate, right? So third pitfall you want to be careful about is uncertainty in the estimate. Um, Unfortunately, a lot of the scientific community tends to focus on, if you have, let's say like this is a number line here and this is zero, what they're oftentimes very interested in is how sure are you that it's, say a positive effect or a negative effect. And so for a lot of people, as long as, if you get an effect that's like this, it's between this big and this big, all right, well, we're pretty sure that it's above zero. So, okay, cool. That's all that people care about a lot of times. Yep, above zero. That's great. You can also have one that looks like this, and people are like, oh, yeah, that's great too. Even though, this is maybe like a really big effect. This is a really tiny effect, let's say. And then all that you end up reporting is this medium one. You say, oh, well, look at this. I got this medium effect, and I'm pretty sure it's above zero. Right? And so you report, hey, look at this medium effect. Sometimes it gets really big and you have like massive uncertainty. And so one famous example was, well, let me actually, before I get into it, I'll tell you in a moment what their actual results were. I'm kind of spoiling a little bit, but it was the study where they wanted to see the effect of kind of intervening and helping uh, kids in Jamaica early in life. And the way they did it is that they did a random selection and stuff. So it was a nice experiment where they went in and they, for 1 hour a week for 2 years, a government worker would come into the person's house and work with both the parent and the kid, so that way the parent could learn some better parenting skills and also learn how to interact with their kid to help them with a more growth mindset or whatever. I don't want to say that. That's not what I actually meant. But help them somehow help them interact with them to be more stimulating or blah blah blah. Right. And so they did this for 2 years. And then for this particular study, they came back after 20 years. They found most of the same subjects, the kids, now all grown up, and they looked at their income. And they wanted to see what was the effect of this intervention from when they were little kids, what did it end up having on their eventual income. And this is a tough thing to do, right? Because of course, income has massive amount of variance. Where some people earn 30,000, some people earn 90,000, some people earn 150,000. It's really skewed to the right also. So let's quickly do some analysis to see, well, okay, suppose that we actually want to do this analysis. How many kids do we need? Right? So let's take a look at it before we actually do anything. So this is titled No Easy Data. So let's suppose that you have, say, the size, so number of kids here is 100. And then for our treatment, let me zoom in on this. And our treatment here is, I just want to make sure I have everything here right. Okay, cool. All right, and so for our treatment, there's going to be, we have to do a NumPy array here, where it's going to be 0 or 1, 0 if you didn't get the treatment, 1 if you did. And then we have to have size over 2 here. So all that I've done here is, treatment. Let me see here, what have I done? np.array, size over 2. Oh, I think I need to put in like parentheses here. Let me see. There we go. I think that's what I had to do. There we go. And so all this is just a bunch of 0 ones, and it's 100 of them. All right, so 50 of them got the treatment, 50 didn't. Now, before we go on, what do we think is actually a reasonable treatment effect? Right? Like, how much do you think that that this treatment will increase their wages by, their income? Like a pretty good effect. I mean, keep in mind, this is like when they're little kids, and we're looking 20 years later, how much their income has been changed by this kind of like 1 hour a week kind of therapy or intervention. And it's kind of and it's, I don't know, this depends on who you are. Maybe you think that a reasonable effect size is only like 5% increase in their income. Maybe you think it's 10%. Maybe you think it's 20. You can try it out. You can try running this with different levels. For right now, I'll do something like incomes are equal to stats.norm.rv. So we're going to draw some random normals where the mean here is equal to treatments is going to be 0.1 times treatments. So in this case, what I'm going to do is I'm going to say that the average person is at, say, 0.1 if they got the treatment and 0 if they didn't, right? So this is going to correspond to like a 10% increase in earnings, all right? And now we got to say, well, what is our uncertainty in this? And in this case, I'm going to say something like, because people can be like up to, I'm going to say something like, people can be up to say like triple their income. So I'm going to do like 1.5 here is what I'm going to use. And, you know, once again, reasonable people will disagree. They'll say different ones are more reasonable numbers, but let's take a look at this real fast. So plot dot scatter. Let's just look at the incomes. Oh, what will I do this against? Well, I think here. Maybe I should do a histogram here. Plot dot hist of incomes. Let's take a look at this. So here's their incomes. You see most of them are around, say, average, and some of them say are, you know, I don't know what that is, like a third, and then versus some of them are much higher. This is actually kind of weird how it looks a little bit skewed there. Let me try running it one more time just to see. All right, there's a little bit more reasonable. And the difference from the treatment is around 0.1. So overall, there's two groups here that I haven't highlighted, right? But really there are two groups here. And they're going to be shifted over by around 0.1, and we need to detect that difference. We can already see that if it's only 10%, because after 20 years, you know, it's going to be hard to detect this, or it's going to be our hunch here, because the shift is pretty small compared to the variance that we have in the population. So let's quickly run this. I'm going to actually just copy some code over that I did for doing this. It's completely straightforward, nothing special here. I just have an alpha plus beta times whether or not you were in the treatment. So it's 0 if you weren't, and it's a 1 if you are. So therefore, this beta here is how much more income you're going to get, right? And alpha is your average income, right? Which should be about 0. And I give it right here where alpha, you know, it has some relatively regular prior there, 0.5. And then the beta here says, okay, we think that the effect could be positive or negative from this intervention, and it could be up to, say, you know, reasonably between minus 50% and plus 50% of your income. But of course, we still have some probability out there for even larger ones. So we run this. Whoa, what if I just done this? There we go. So now we run this. And now let's look at our posterior. So we're just do az.summary posterior. So with this 10% one, let's just run this. We see that our beta, this is the one we're interested in. Our best guess, if we had to guess one number, would be that it gave a 20% increase, which is actually above what it was. But we aren't sure, right? In fact, our reasonable interval here says that it's somewhere between a 22% decrease up to a 62% increase in earnings. That's a huge range. It's plus or minus 40%, which is huge in practical terms, right? So we could try running this a couple more times if we wanted with new data. You know, let's try it out one more time just to kind of get a feel for it. But in general, what you're always going to see is that based on the uncertainty levels of the data and such, we're always going to be about plus or minus 40%. So here's one where it's the beta was 0.4, which is around 40% increase. And we're, hey, look at this. We're pretty sure it's positive, right? According to this, because it's either a 1% increase up to an 80% increase. Right. And of course, you think about that like, okay, we do this intervention, this big intervention, and we say, okay, in the long run, it could increase their income by 1%. That's reasonable. But what also is reasonable is an 80% increase, almost doubling their income. That's a massive difference between something that's almost 0 versus something that's a huge, almost doubling of their income. And so from this, if you only have 100 subjects here, it's going to be hard to really get anything useful, even if it has a real effect. And you know, the question is 10% a small effect or a large effect? I think that's pretty large, because if you can do this little intervention and increase people's income by 10%, that's pretty good. So first question that we got to ask, though, is what about if we had 1,000 real fast? Let me just see. If we had 1,000, could we more reliably estimate this? Let's take a look. Well, let's run it. I just generated a new one with 1,000. And now you can see that now our beta says 20%, but we're between around 4% and 33%. So you can see it's closed down on the variance a lot, having this, you know, 10 times as much data. And, you know, I mean, in this case, you can at least say it's a small to moderate effect, to pretty large, actually. 33% is pretty big for such a seemingly small intervention. So real fast, though, what did they actually do? Well, it depends on where you look. In their first version of their paper, they said that they had estimated it to be um, I believe it was a 42% increase in earnings. Huge. And then when you looked at what their actual, they didn't actually state their interval, but because they gave their t-values and things like that, you could backwards induce it. It turned out their interval was somewhere between, let's see, I have this written down here, 2% up to 98% increase in earnings. That was their kind of like their uncertainty interval. So it's either almost nothing or a absolutely gobsmackingly huge effect. And they had no idea what it was between those two values. And yet all they really reported was 42%. Now, in a later paper, which is the one that I'll link, they end up somehow revising their analysis, and then it ended up being down to like I think a 25% increase, but it was between pretty much about a 0 and a 50%, which is still just enormous. And the reason why is that they only had 100 subjects thereabout. By the end of it, they were only had around 100, so it was actually very close to the analysis we just kind of simulated there. Where if it was a 10% increase, you wouldn't really know what it was. You could be getting large effects in either direction. It's hard to say. And your uncertainty would cover a lot of different possible values. Is my point. And so what you would say is that they didn't really have much power or precision in their estimate because unfortunately, this is a costly intervention. They couldn't do it on thousands or tens of thousands of people because it actually involved people going to their homes every week to help them and stuff for a couple years. And then you had to keep track of everyone. You had to measure them 20 years later. I mean, it was a really tough experiment. They did the best they could. But at the end of the day, this uncertainty interval is almost just too large to really be are you really going to make a policy off of this? We're like, yeah, we're pretty sure it's somewhere between almost zero and enormous. It's like, well, thanks, pal. You can really make a lot of really good decisions off of that. So, I mean, it's kind of rough, right? But these are hard problems. And any problem that you try to do, any serious problem you're trying to do is usually a hard problem. So you want to be aware of some of these pitfalls. And you might want to do, we'll talk about this some throughout the semester, which is doing some extra power analysis where what you do is you do simulations like I just did. I said, okay, well, how many subjects do I need to actually try to estimate this thing reliably? What kind of variance am I expecting as far as my final estimate? Will this actually be a very useful estimate, or do I need more samples, or do I need to somehow get a larger treatment effect or reduce the variance somehow? How am I going to try to do this? And so it's an interesting problem, right? And so you can do a lot of cool power analysis. You can also do retroactive power analysis, where you take your posterior and you do the simulations based off your posterior and try to say, well, based on what I did, how kind of like how likely was this large effect that I detected, and things like that. So it's kind of interesting. And the last pitfall I want to talk about is just the garden of forking paths, also called p hacking. But I don't tend to use that one, garden of forking paths. And the idea of this one is sometimes when you're doing analysis, you have a lot of choices. Well, in every analysis, you have choices. Do I want to leave out certain subjects because I feel like they're outliers? Which regression do I want to run? What terms should I include? Now, of course, if you're doing causal analysis, pretty clear, or at least it's easier. But it's things like, okay, am I interested in whether or not women uh, did things differently than men? Right? That's a choice. You get to choose whether or not to look into that. It might not be your central question, but maybe a secondary question. If you're looking at COVID drugs, should you do whether or not it reduces death? Should you determine, but there's other things like probability of ending up on a ventilator versus probability of death, how long it takes for you to get out of the hospital, how long to recovery. There's a lot of different possible things that you could measure. And lots of ways where, for example, in the previous study we saw where it was the distance to the homeless shelter, they grouped them into 4 bins. How did they determine those 4 bins? 0 to 2 kilometers, 2 to 5, 5 to 10, 10 to 20. They could have chosen different sets of numbers for binning. There's a lot of different choices in all your analysis. And if you're not careful, if you look at the data ahead of time and you kind of decide how you want to do it based on what the data you see, you can accidentally, pretty much just by looking at it, kind of run a regression in your head and go, oh, I want to run this regression. And sure enough, you run it and you find some big effect, but it might just be noise because you didn't really actually have priors that said that that was a reasonable thing to look at. And so this happens all the time, actually, in a lot of especially in a lot of the sociology and psychology papers, where at least historically, where they get led down this garden of forking paths of different possible analyses they could do, and they always end up leading themselves to one where they find some big effects that are actually really uncertain. And but then they report on those and kind of work their theory. They kind of do it backwards, where rather than starting with the theory and coming up with the test, they come up with they look at what they find like the biggest effect for, and then they retroactively kind of come up with your brain kind of retroactively comes up with a theory to justify why that's the case, and then they use it to confirm it. And it's okay to do exploratory analysis, but you need to explain that, hey, look, I'm kind of just looking at this data and I find some of these things. Let's do some extra analysis with more data in the future to confirm this or not. But sometimes these are portrayed as, look at this, we expected this big effect and we found it, but really it was kind of something that had happened after the fact. So it's not quite truthful. And you do this completely unintentionally. I know I've done this before with some of my models where I will have, and this, like I've run a computational model, not a statistical one, and I've gotten some surprising result out of it. Once again, I felt for the surprise here. And it was something where like I didn't expect it at all. I said, "Oh boy, look at how cool this is!" And I showed it to Dr. Zenti or my advisor or whatnot, and I said, "Oh, look at all this cool stuff, really surprising results." And then we're like, "Well, why on earth does this happen?" And I came up with some cool story on why this is actually some weird interaction I didn't expect. And then next week I had to kind of sulk in there, sheepishly and go, "Yeah, I found a bug in my code. It turns out that whole thing is wrong, and it was exactly what we expected at the beginning." Surprising results are exciting, but they're oftentimes you should be kind of skeptical of them. And so, I've made the mistake too, where I see some result and then I backwards come up with some sort of explanation or justification for it. It's really easy for your brain to just find patterns that aren't there. So you want to be careful and have some theory ahead of time, and just be really careful on how you do your analysis. So I want to show you just one very famous one really quickly, and then we'll call it. We'll stop it here, and then I'll come back and I'll do a second part afterwards, which will be doing the actual analysis as far as categorical variables and identification. So I'll do that in the next video, because this one's already an hour and a half long. So that's probably going to take another 45 minutes or so. So this last paper I want to show you guys is right here. This is a classic one. This is actually one. This one's been cited like 1,000 times. It's a very famous paper by Daryl Ben, and it's Feeling the Future: Experimental Evidence for anomalous retroactive influences on cognition and affect. This is the famous ESP paper, where this guy showed that people could predict the future, essentially. All right. And what he did was he had these 9 different experiments where it was there were all variations on this simple thing where it's like, okay, here are 2 choices you have, left or right, pick one. And then they would pick one, and in some of the experiments, for example, in one of these, they were said, okay, behind one of them is like a picture of a dollar bill, and behind the other one, there's nothing, right? And then it's like, oh, well, I want to get the dollar bill, so I have to try to predict which one it is. And they choose one, and then the computer would actually randomly choose which one the dollar bill picture was behind, and then they'd reveal it. And so if you could somehow predict the future before the random number generator actually the computer actually chose which one was behind there, then you would be able to reliably pick the one with the dollar bill behind it. Now we found out there was no effect for that. But it turns out he did another variant where instead of a dollar bill, this is legit here, he had erotic pictures, somehow some sort of nudes or something, I don't know. And by golly, people could actually pick better than 50% chance the picture, the side which was eventually going to be shown to have the picture behind it. And how well could they tell it? Well, I think that if you look at it, it's not nearly as much like. So here we go. You can see. Oh, let me switch to it here. Here we go. So Feeling the Future: Experimental Evidence of anomalous retroactive influences on cognition and affect. So here we go. Here's like the first experiment. He did it across like 9 experiments, found it robustly and like all of them pretty much, right? This was like really strong one, like 1,000. Look at this. I mean, look at this. So they say This is pretty impressive. This article reports 9 experiments involving more than 1,000 participants that test the retroactive influence by time reversing well-established psychological effects so that the individual's responses are obtained before the causal stimulus events occur. So this is predicting the future here. And he sits there and he goes through and he shows it across all 9 experiments. They found mean effect size that was pretty significant. All but one of the experiments yielded statistically significant results. Which is, on average, you could say that you're with 95% confidence that it's positive, right? And then the individual difference, blah blah blah, and then they talk about people who have extroversion versus, or also like people who are like erotically inclined, I think is what it says, found correlations in 5 of the 9 experiments, right? So it goes on and talks about how, look at this. I mean, we have lots of people. This thing is legit. And so anyway, I'm not going to go through the whole thing because it's just garbage. This is the one I'm not afraid to insult. All right. I think a lot of the other ones, they did really, they put in the good effort. They did a good work. This guy, I mean, he's just whatever. Not gonna give him any compliments. So he goes through. He shows them. Look at this. Several of the pictures contain erotic images. Oh boy. Okay. Go for it. And so, he finds out at the end of the day. Here we go. Results in discussion. Somewhere we'll find the thing here. Here we go. Across all 100 sessions, participants correctly identified the future position of the erotic pictures significantly more frequently than 50% at 53.1%. And then the t-statistic p-value of 0.01. So that means that if they had a 99% credible region, which they use a confidence interval, which is different, but it wouldn't contain 0. It was all the way off there. But you'll notice that it's actually quite close to the 95, but whatever. In contrast, their hit rate for non-erotic pictures did not differ significantly from chance, right? So, apparently he has some theory that says that they'll be able to do it for the erotic pictures, but not for the dollar signs or whatever, the neutral or the positive or the negative images or whatever, None of that stuff worked. Because you see right here, which is kind of weird. He did trials with the erotic pictures. He did trials with negative pictures. Presumably they're going to try to pick the one that doesn't have it, would be my guess. And then also ones neutral ones. And, so you can sit there and already see in his design here that he has the neutral where you expect that, okay, they'll pick whichever one, it doesn't matter. For the erotic ones where they want to aim for it, and for the negative ones where they probably want to avoid it, right? And so you would expect that sort of thing. But then when you actually look at his data, you see there's not really any effect from the negative pictures or the neutral pictures. And also not even for romantic, but not non-erotic pictures. None of those had any significant effect. The neutral one he probably expected, but the negative and non-erotic ones, I bet you ahead of time he had a theory saying, hey, I think that they might avoid the negative ones or aim for the romantic ones. But because he didn't find any significant difference, they were right around 50%, he just says, well, those weren't significant, but my theory here was that the erotic ones were going to get the effect, because that's the only one I found that actually seemed to be actually quite different from, where they happen to do better. But you can imagine that if you redid this whole thing, but instead this one happened to be around 50 and the negative one was 47 or higher or something, he would have come up with some story for why that was the case. Now, you might not believe me. You're saying, hey, you're not giving this guy enough credit. You're kind of assuming bad intentions, or, him kind of going back and changing what this stuff was. Right? But he's actually not entirely, so he has all these experiments, but he's actually somewhat open about this stuff at the end. Or if you keep going through all of it, and some of this stuff is really crazy with like subliminal messaging on top of things, like future subliminal messaging led them to do it, but not if it was too long, too much subliminal, because then they got bored of it, or it was all sorts of weirdo stuff that he came up with. But anyway, there was a lot of just so stories. But at the very end of it, it's actually kind of interesting. He actually talks about some of the biases that lead to bad results, and that he's not, and say why he's not following, that he's actually legit. They're talking about the file drawer bias, which is always saying that if you find something that's not significant, you just don't talk about it. You don't submit that. right, into a journal because they aren't going to want it because not even significant results. Well, he says that, you know what, to be honest with you guys, I've tried to report everything, but there are three of them, which I believe he says three of them, which he didn't report. So he says, I can identify three sets of findings omitted from this report so far that should be mentioned. So he's very open and upfront about this, right? And so for several individual differences, he tried some stuff involving I forget, like superliminal or whatnot. So he was saying pretty much he did a lot of pilots with different stuff, and then he kind of went with the ones that ended up working and kind of abandoned some of the ones that weren't really working. And in some of them he says, yeah, you know, and in fact, I should have known it wasn't going to work ahead of time. I was kind of foolish to do it. You know, as I was warned in a convention, this superliminal exposes is not going to work, but you know, he did it anyway, and then he regretted it. And then he talks about issues of replication right here, where if you're going to try to do this again, are you going to find the same results? And he actually goes through, and it's kind of weird. He tries to give all these explanations for why it is that, well, and it is true that if you find something that's just barely, you know, straddles zero, right, where the left side of your confidence interval or whatnot is zero, you run this again, and what is either going to be a little bit to the right or a little bit to the left, right? 50-50 chance either direction. If it goes left, it's now no longer going to, you know, it's now going to be either, you know, not going to be, you're not going to be really sure that it's positive. And so he says, you know, if you try to replicate this, there's a 50 for a lot of these, since they're right on the edge here, you're going to replicate it in half the time, you're not going to find it. You know, he talks about this. And he says, you know, and I'm not trying to lower my expectations. I believe all this stuff is real and blah, blah, blah. But I just want to, you know, you need to set your expectations accordingly. In fact, of course, if you try to replicate this stuff, you won't find anything. People have tried, of course, it doesn't find anything. But what happened here is that you go back, and it's really instructive to actually read this paper because you can go back and see how it might not even been like, you know, like I said, malicious or anything or deceptive, but he could have just possibly fooled himself because he happens to find one result out of, you know, a lot of different tests. I'm trying to remember, I think it was in number 6 here. He finds one case where when he repeats it 4 times, 6 times, or 8 times, he didn't find anything significant. But on sessions where there were 10 exposures, aha, now suddenly they were predicting only 46.8, which was significant. And it's barely significant. You know, it's this huge error bar again, right? But he just happens to get just barely onto the side of negative, showing that they avoid it more. He goes, aha, this effect suddenly goes full on interpretation and everything. Not, well, you know, I tested 10 things and I just happened to find one by chance that, you know, noisy measure. I happened to get one that was a little bit on one side where he measured 20 things or 30 things. Nobody even knows how many he measured. He hasn't ever actually produced the data. Um, but, you know, and he goes, okay, this effect can be interpreted as retroactive induction of boredom. So they got bored when they did it 10 times. That's what caused this issue. Even though he didn't see it in the previous experiment or any of the previous 4 experiments, he didn't find it. But this one he did. So therefore, boom, he found a new effect. Look at this, a nice, significant serendipitous finding. And of course, we all know, though, that it's not really there. He fooled himself, essentially, or is trying to fool us. I don't know which. I'll give him the benefit of the doubt and fooled himself. And so then in the future, he tries to do it some more and blah, blah, blah. You know, I'm not going to go through it all.